Hello guys, welcome back to my channel Gamma Digamma. So in the last video I believe I explained some properties of the Dirac Delta, and the video before that I introduced the Dirac Delta. So in this video I would like to talk a little about the applications in terms of distributions of three different kinds: singular or point mass distributions, sheet distributions, and line distributions. So let's get started. Mass distributions, I briefly talked about them in the last video. So if you have a density function in the Cartesian system, we will talk about other systems later. We have m naught, say the point mass is at the origin. We'll have delta x, delta y, delta z. This will only be 1 when all of these deltas basically integrate out to give 1. So we want all of the deltas to be satisfied. Any one of them is not satisfied, it will just give a 0 in the integral. And so the total mass, capital M, is equal to volume integral of this density function over, say, all space V, which is density function is m naught delta x, delta y, delta z. Since this is a Cartesian coordinate system, we can write the d tau as dx, dy, dz. So negative epsilon plus epsilon, we're taking an arbitrarily small neighborhood for each of those, dx, dy, and dz, because the 0 of the delta, all the three deltas, is at the origin. So we're taking an arbitrary neighborhood around the origin. M naught delta x, delta y, delta z. We can use a Fubini's theorem. Take the delta x with the dx, delta y with the dy, delta z with the dz, and all of those integrate out by the property or the definition of the Dirac delta to give 1, leaving us with just a myriad m naught. That is the total mass of the entire system, because the system just consists of a point mass at the origin. So it clearly makes sense. Okay, we know that, say, dx of delta x is 1. So we can conclude that delta x has units of 1 over length, because dx is a length element. So 1 over length times length gives us, basically, in terms of dimensions, a dimensionless quantity, which is a number, in this case 1. So in the SI system this will be meter inverse, and you can see that this makes sense. Do a sanity check. Density function xyz is given by m naught delta x, delta y, delta z. This, according to this logic, should be mass over length cubed, which is precisely the units or the dimension of density. So this clearly makes sense. In this case we're just talking of mass density, no other density. What if we want to generalize this idea? Instead of having the point mass at 0, having it at arbitrary point x naught, y naught, and z naught, we can do this. So m naught is the mass of the point mass, delta x minus x naught, y minus y naught, z minus z naught. So just shift those deltas by this point. Okay, this was basically sort of a recap, and this is pretty much what you need to know for point mass distributions in the Cartesian coordinate system. Let's talk about some other systems now. Okay, let's talk about the cylindrical system. This is sort of an example. So rho naught is x naught squared plus y naught squared, again using the same x naught, y naught, z naught reference point as before. So we have a reference radius rho naught, a reference angle which will be given by inverse tangent of y naught over x naught, and z naught which is precisely z naught. So what will be the density function, in terms of all these Dirac deltas? Because it's a point, so we need 3 Dirac deltas. I hope you know this from the last video. Our natural guess, something kind of trying to ape what we had on top, something like m naught, that's going to stay the same, delta rho minus rho naught, delta phi minus phi naught, delta z minus z naught. Okay, fine. If this is the case, let's just check. We want integral over volume v, volume integral of the density, to basically just give us a mass, right? The total mass of the system. So it should just be a mass value, nothing else. So if you just integrate, the volume element in cylindrical is d rho, rho d phi, dz, and then just plug everything in. So m naught delta rho minus rho naught, phi minus phi naught, z minus z naught. And then what we notice is, if you just look at the rho integral, take an arbitrarily small neighborhood around rho naught, you have d rho, rho delta rho minus rho naught. If you calculate this just becomes rho naught by the property that I discussed in the last video of the Dirac delta. So this means everything else just becomes 1 because of the definition of the Dirac delta. This integral on its own is, say, d tau rho sub m is rho naught m naught, which is not equal to the total mass, because rho naught has units length, mass has units of mass, this has units of mass, so the dimensions aren't clearly matching on both sides. So there's some issue going on. How do we solve this issue? Well, notice that there's this like lingering rho factor in this integral that's basically messing the integral calculation. What we can do is we can just redefine our sort of density function to be m naught over rho, delta rho minus rho naught, delta phi minus phi naught, z minus z naught. If you integrate this out, you notice that the rho, because of this volume element, and this rho sort of cancel out, thus eliminating this rho in the integral I've bulleted here. So we just get a 1 in place of rho naught, which is a desirable answer because it removes the rho naught here and we get the total mass as m naught. Let me sort of try to generalize this idea a little bit. Okay, so in general, I'm trying to generalize. This is a little brave, but because I haven't sketched a very detailed proof. My volume element in a general curvilinear system is h1, h2, h3, dq1, dq2, dq3. This is for free variables q1, q2, and q3 in a general orthogonal curvilinear system, orthonormal curvilinear system. Check one of the videos that I've made, say like in the past couple of weeks, if you don't know what I'm talking about. Assume the mass is located at, it's a point mass, so it will be at one point, q1 naught, q2 naught, and q3 naught. So we have the density function in this new system to just be m naught, because the mass value was fixed, delta q1 minus q1 naught, over h1, q2 minus q2 naught, scaling factor h2, q3 minus q3 naught, scaling factor h3. Okay, the compact way of writing it, and this will probably be extremely useful if you're like writing a research paper in the future. If you use this compact notation, everyone understands, everyone who knows what you're talking about, you save a lot of space. So delta cubed, or say delta 3 r minus r now, which actually means that there's like 3 deltas. Instead of having just, you know, q1, q2, q3 separate, we are vectoring it up as a position vector, which is basically defined as delta q1 minus q1 naught h1, delta q2 minus q2 naught h2, delta q3 minus q3 naught h3. Well, this is the general curvilinear or orthonormal coordinate system. In the Cartesian case, you can easily just plug the appropriate values in this expression. All the scaling factors become 1. So our sort of Dirac Delta triplet in the Cartesian system just becomes x minus x naught, y minus y naught, z minus z naught, which clearly agreed with what we had over here in yellow, just here in orange. So what we can do is, using this compact notation, because this notation, you know, introduces a vector. A vector is coordinate system invariant. I'm not talking about the components or the basis vectors, the vector itself. So one important point is that regardless of the system, several point masses with mass m sub I can be represented by this this grand density function. It's the sum from, say, I to some value m sub I, Dirac delta triplet r minus r sub I. So so whatever coordinate system you're in, just plug in for your position vector, and also, you know, substitute appropriately using this formula for the delta triplet, and then you'll be done. You can just implement it. So the total mass can be just expressed as a volume integral over V of these guys, m sub I of this triplet, delta triplet. This is the most general way of expressing this mass distribution of several collective point masses. The total mass will just be a sum of the masses, individual masses. So we sort of, you know, sorted this out. So this is the really compact general notation. This will save you a lot of space and trouble. I really like the elegance in this. I hope you see it too. Okay, moving on to sheet distributions. We assume we have a two-dimensional planar sheet, so it lies in like one plane. Again, we are working in R3 in 3 dimensions of uniform mass per unit area value. So this is some areal density, if you want to think about it, sigma naught in the z is equal to z naught plane. Okay, so the way I think about these planes or these sheets is that, well, I don't like to use this notation because I haven't talked about them formally. Is there two manifolds in three-dimensional space. Again, this is really, the idea of manifold is like a complicated mathematical definition of something, but what I mean is that for three variables you have two freedoms of movement, one constraint, and that constraint is usually, at least the way we are thinking of these things, is going to be an equation. So an equation like this, say z is equal to z naught. So we are constraining z is equal to z naught. X and y can do whatever the hell they want. So x and y, again I'm using linear algebra terminology, will span the entire like xy plane, but all of this entire plane that they will span, so practically infinite, will be located at a constant value of z naught. It can't go anywhere. It's trapped in the z is equal to z naught sort of height from the origin. Okay, so if you have something like this, then one guess for your density function, when I mean density, it's volume density, it's going to be x, y, z. We'll have sigma naught delta z minus z naught. So think about it this way: for say a one manifold, or rather a zero manifold, which was like a point, we had like three levels of constraint, right? We had everything like we had x constraint, y constraint, and z constraint, which sort of narrowed down to one point. So we needed three deltas. In this case, we have one constraint, so we need one delta. So constraint, number of constraints is equal to number of like Dirac deltas you need to sort of fabricate this density function. Let's try to check if this is the answer, the appropriate density function. So the best way of doing it is basically integrating. So since this was sort of sigma naught was an area distribution, we can integrate over the entire area, which is the entire xy plane spanned by the x and y coordinates. So we just get sigma naught and is equal to volume integral of the volume element and the volume density. So I mean, all of these guys, surface area density integrated with surface area is equal to volume density integrated with respect to volume, because all of them, they just are forms of the total mass. Okay, so since we're in the xy plane, parameterize it appropriately to get this sort of double integral dx dy with a sigma naught up front, because that was uniform, luckily, otherwise it would have been hard, this integration. Now the volume element, we had proposed, so this will be dx dy dz. Let's go in order. We had proposed this, so just plug that in and check whether left hand side and right hand side are being satisfied here. Okay, and clearly they are, because integrate this z minus z naught, you're integrating over all space, so z naught will be included. This integral goes to 1, so the z, all of the z dependence just goes away. You just have the dx dy sigma naught, which agrees on basically both sides. So this is precisely the total mass of the system. Now consider some sheet in y equals x plane. So again, the equation, the equation or the constraint we have, always write that down as y is equal to x. How you make a delta is sort of set that equation to 0 and then just delta both sides. That's the way I like to think about this. So this is the delta we need. So now just construct a density function around that delta So you can just do that. Since we know it has a uniform area density, sigma naught times that delta. So this is our guess. This is our guess. Let me say this is not actually right, but what happened was the guess we used here on the z plane, it just turned out to be right. We were lucky. In general, if the sort of the sheet is in one plane entirely the z, entirely the x, or entirely the y, then these guesses will work, the initial guesses will work. Otherwise we're gonna have to do something, and I'm gonna explain what we have to do in just a bit. Okay, so what we can do is we can basically check our guess with an integral and account for like the missing factors, like we did in the on the previous page for cylindrical system deltas. So surface integral of sigma naught, because again use the same approach. Surface integral of the surface density is equal to volume integral of the volume density. So integral over like the entire volume. Before doing the volume, let's just look at what this is. So this is, say, it's some ds and dz, the way I parameterize it. So this ds is in the y is equal to x direction. Z is just increasing because there was no constraint on z. Sigma naught, this is just parameterization. I will make a video on double and triple integrals. I hope that will clear things out. For now, just go with it. So the ds is in the y is equal to x plane. Now what we can do is ds is square root dx squared plus dy squared. This is basically arc length formula from single variable calc. The way I like to think about this is construct like a Cartesian, which is like a scaffolding. Okay, say assume this is like y is equal to x, so this is probably a really accurate drawing. So say ds is like some chunk on this line. Dx is like the chunk on the x direction basically, so this is dx. Dy is like this vertical chunk. So you clearly see you can do like a Pythagoras theorem on this small triangle here that I've sort of shaded out, and you get this formula. So it shouldn't be too hard to visualize. Now just plug everything in. We know y is equal to x along this line, so differentiate both sides. We'll have dy is equal to dx. So what I'm doing is, instead of I'm changing the dy to a dx, just substituting, I get square root of 2 dx, that is ds. Just substitute and we just get a regular double integral now. I mean, see, all this is because of the parameterization we had to choose, which was different. In the previous case, the parameterization was easy. Just take the plane it is on, which is unconstrained. So d sigma naught is basically equal to square root 2 dx dz sigma naught. Okay, and this guy is precisely equal to the volume integral. So we just plug in our guess here. Sigma naught delta y minus x. So if you like integrate in the dy, this y is equal to x will be included naturally. So we just have dx integral and like the dz integral sigma naught. So you notice both of these should be equal, right? Because both of them just represent the total mass. Now there's like a sort of contradiction, and the contradiction is because of this root 2 factor, which means our guess initially was incomplete, more than wrong. It's constructive to say it was incomplete. So the right guess, or at least the right answer, or rather general way of going about guessing is take the density function equal to some question mark factor sigma naught and then that delta. Because now if you sort of integrate this, you have space for improvement, you have space for some correction. Dx dy dz sigma naught question mark delta y minus x. So you sort of integrate it like before, dx dz question mark sigma naught. You basically just get, after you integrate sort of this area part, d sigma sigma naught, you get ds dz sigma naught just like before, which we knew was square root 2 dx dz sigma naught, which means our question mark was nothing but square root of 2. This means that our right guess, or the right answer for the density of this sheet, square root 2 sigma naught Dirac delta y minus x. This is the right answer. If you integrate this, you'll clearly see the right answer. So the idea of this was to sort of make you see that we need a question mark whenever we are guessing, and not just for these sheet distributions, but you'll see also for line distributions that I will do on the next page shortly. So always put like a question mark in, although it may be on one plane and it'll just work out, but just to be safe, the right way of doing it is putting a question mark and then substituting in by doing the area integral and equating that to the volume integral with that question mark factor, and then sort of comparing both sides. Because you're integrating over the same region, you can find the value of what the question mark should take. The question mark should ideally remain inside the integral because it could also be a variable. I didn't cover that case, but I will soon. We were lucky we got square root of 2. If it was some atrocious function, not y is equal to x, but like y is equal to cosine x or hyperbolic cosine of x, then we would really be in a little trouble, and the integration wouldn't be that easy either. So let's do some line distributions now. See you on a fresh page. Okay, so like we talked about surface area density sigma naughts, we have linear mass densities now to talk about. Say sigma naughts, which will be uniform if it's uniform, and for these kinds of questions it will be uniform. Otherwise, just denote it as sigma sub m on some variable. And what we're going to do, total mass of the system, again set the volume integral to equal to the line integral. So the volume integral of the volume density, which is a scalar field, is equal to the line integral of the linear mass density function, which is again a scalar field, no vectors here. So consider some sort of like a parabolic curve in z is equal to 0 plane. So this is a one manifold in three-dimensional space, which means you have two constraints, right? 3 minus 1, so two constraints, which means we need two deltas. So sort of this should sort of convince you a little bit. This is in one plane. This will always be in one. The curve will always be in one plane. Okay. What else? Okay, time for a guess. The equation for this is y is equal to cx squared. So that's enough to help us formulate an initial guess. And taking inspiration from our sheet distributions, put a question mark. This entire thing has uniform linear mass density lambda naught, so just put that in. Delta y minus cx squared, delta z, because we are in the z is equal to 0 plane. Everywhere else this sort of the curve is not defined. So now the arc length, like before, is going to be do a proper Euclidean distance norm. So that's how you do it. Again, the diagram for this, you can sort of take inspiration from before. It's a bit like this. You have some curve. I take some ds element on the curve, some line element on the curve. This is dy. Dx, and dz is like sort of like the distance like above, or how much this guy is sort of rising. This small piece is sort of, you know, raised. In this case it's like 0 because it's in the plane. Okay, so I hope that that picture helped a little. Not too sure, but whatever works for you. So we have z is equal to 0, y is equal to cx squared. These are our two constraint equations, so make use of them. These are extremely important. If you notice, you know, in this example, the last example, not just for like formulating the deltas, but also for like taking this distance norm. So ds is 1 plus, differentiate this guy, you have 2cx, the whole thing squared is 4c squared x squared. I have a dx factor, because dy just is 2cx dx. So our volume integral is just this, which becomes dx 1 plus 4c squared x squared. This is the line integral part of it, because you parameterize this curve as a ds. I mean, look at on top, like ds and this linear mass density. So that ds is precisely this. We just parameterized this curve and made it an integral with respect to x. Plus we also know by definition that dz delta z is 1. So on in the top guy, this delta z, the z integral goes to 1. All we're left with is, I believe, well, even this delta y minus cx squared leaves the y integral to 1. So all we have is dx, this question mark, lambda naught is equal to dx square root 1 plus 4c squared x squared. This is equating the volume integral and the line integral. We notice that this question mark factor 1 plus 4 c squared x squared. Okay, if this were, say, in like z is equal to y, or some weird other plane, then, you know, it would be a little more difficult, but it's not. It's usually these guys are easy. Okay, so with the value of the question mark known, we can find the density function as square root of 1 plus 4 c squared x squared. Think of this as like a normalization factor, and we have a lambda naught delta c y minus cx squared delta z. Another way of doing it, and this is like a really weird sort of unorthodox method, I prefer the one on top, is sort of, you know, taking basically flipping the argument, because the delta is even, and using the property of basically argument times something, you get delta of y minus square root y over c, y plus square root y over c. I just divided like the inside argument by c, and then, you know, converted that using an appropriate identity from the last video, and then just wrote it as a difference of squares. And then using sort of the quadratic input property of the Dirac delta, I can have 1 over square root 4 cy dx delta x minus square root y over c plus delta x plus square root y over c. So we have basically two delta functions that are added together. We have sum of deltas, and using that, you can conclude that sort of this is the answer. So I mean, just food for thought. I again prefer the method on top. It's pretty nice. I really like it. It's just sequence. There's a nice sequence to it, and it's easy to understand. Okay, just to conclude, I'll just tell you why we needed a delta for the different distributions. Is because for like a line, we have a linear mass distribution. For a sheet, we have an area mass distribution, and for a volume, we have a volume mass distribution. The issue is we need to keep track of all these things depending on what kind of object we're actually considering. And of course, a point mass has a Dirac delta directly. So it actually depends on, like, say, what we're talking about usually. And we need to sort of, choose them wisely. We need to keep track of, each of them for different objects. Instead of this, using the Dirac deltas for these two cases especially, the line distribution and the sheet distribution, if we use deltas for them, we can express these two distributions by just using a density. Same thing with a point, just the density is equal to the Dirac delta in that case. So a volume density can represent anything. It can be a one manifold like a curve, a two manifold like a sheet, or a zero manifold like this point. So we have a uniformity in terms of what function or what type of function to choose. We just use the volume density function. Sort of use the deltas to sort of eliminate those other integrals, because say this curve is like in like the x plane or something, then or like if you're integrating dx entirely, then and if you sort of use a volume density for that, for the volume integral there's all these dy dz. You sort of want to get rid of those because you want to set that equal to a line integral, right? So the Dirac delta does that job for you. So you can use the delta to eliminate like extra integrals like dy dz in the case of the line in the x direction. So that's the way like deltas are really useful. Again, this is not just true for like mass distributions. You can do this for like charge distributions or any other kinds of distributions, you name it. Even probability distributions, when you have, say, wave functions, stuff like that, or probability densities, stuff like that, current distributions, whatever that means. So yeah, this idea is sort of, I've become specific for this case in terms of masses, but you can sort of generalize it by just doing appropriate changes. So I think that's it for this video. I hope you enjoyed it. Stay tuned for more content. Please like, share and subscribe to my channel, guys. Recommend to your friends, spread the word of Gamma Di Gamma, and in the meantime, keep doing math, stay home, and peace out. Stay tuned for more content.